Math 1343, testing means. Testing two population means, critical value approach. Just like in the previous series of videos, when we transitioned from testing one population proportion to testing the difference in two population proportions, we only have to make a minor change or two as we transition from testing one population mean to testing the difference in two population means. We'll go over the example behind me in just a moment, but I just wanted to briefly go over what those changes are. For testing two means using the critical value approach, our first step, as expected, is still to state the hypotheses. But because we're testing two means, there will be two mu's, mu1 and mu2. And our hypotheses will be comparing whether or not they're equal or whether or not one of them is greater than the other. Our second step, finding the regions in the critical value or values, is the same as before. The significance level will represent the area of the tail or tails as dictated by the alternative hypothesis. And we will use the t-distribution. But because we have two populations, we'll have two samples and therefore two sample sizes, which means how do we know which one to use to calculate the degrees of freedom to find the critical value using the t-chart? Well, the degrees of freedom is the minimum of n1 minus 1 and n2 minus 1. Think of it this way. If there were one population, the degrees of freedom would be sample size minus 1. But now that we have two populations, we basically calculate both of their samples' degrees of freedom and then use the smaller of the two. I regret to say that this is not consistent across statistics. I've taught in another book that said instead of using the minimum degrees of freedom, you use the sum of the degrees of freedom, but that's not what we're going to do in this particular book that I'm referencing while I'm teaching this class. So our degrees of freedom will just be the minimum of the degrees of freedom from the first sample or the degrees of freedom from the second sample. As for the calculation of the test statistic, the standard error formula is kind of like the previous one, but a little junkier. It's a square root with a sum inside of it, and on either side of the sum is a fraction. But for each fraction, the numerator is the standard deviation squared, and the denominator is the sample size. So the square of the first standard deviation over the first sample size, plus the square of the second standard deviation over the second sample size, and then the square root of that whole sum. So the last thing you do there is calculate the square root. Then to calculate the test statistic, we simply calculate the difference between our sample means and then divide it by the standard error. And then after that, it's business as usual. Make a decision, answer the question. Let's take a look at this problem. An ecologist wants to study the effect pollutants on potato. I left out a word. An ecologist wants to study the effect pollutants have on potato production. In N1 equals 30 acres of land unaffected by pollutants, the mean yield is X bar 1 equals 10.2 tons per acre, with a standard deviation of S1 equals 0.35 tons per acre. That may sound like a lot, but I actually searched online to see what an average yield would be for an acre of potatoes. In N2 equals 12 acres of land affected by pollutants, she measured X bar 2 equals 8.1 tons per acre, so clearly less than the other one, with S2 equals 0.24 tons per acre. Test if unpolluted land yields more potatoes. Can we conclude polluted land yields fewer potatoes? It's funny because the thing we're testing sounds the opposite of what we're being asked to conclude, but that's perfectly acceptable. All right, let's go through the steps, starting with state the hypotheses. Let's draw a line here separating the problem from the work. All right, step 1, state the hypotheses. H0 with a colon for the null, HA with a colon for the alternative. All right, so what are our hypotheses going to be? Well, one thing we're being asked is Actually, you know what? I didn't want to conclude, let me rephrase, I'm sorry. I don't know why I wrote the last question the way I did. Can we conclude polluted land yields fewer potatoes? I wanted to ask, can we conclude unpolluted land yields more potatoes? Which makes perfect sense because that's in alignment with what we're being asked to test. The real reason I changed it is a little more technical than that, but let's just pretend it said that the whole time. All right, so test if unpolluted land yields more potatoes. If we're going to do this, we need to figure out which subscript means what, but that's pretty clear by the context of the problem. A subscript of 1 is measuring things for unaffected land, and a subscript of 2 is measuring things for affected land. So when we're being asked to test if unpolluted land yields more potatoes, when we're being asked to test this, we're being asked to test if the mean yield for unpolluted land, which is the 1 subscript, so mu1, yields more, so that average is greater than, the yield for unpolluted land, which should be mu2. So we need to test if mu1 is greater than mu2, if unpolluted land yields more potatoes than polluted land. Is that the null or the alternative? Well, it doesn't permit equality because it says more. If it said at least, then it would have been greater than or equal to. But when it says more, that is strictly greater than, does not permit equality. That is the alternative hypothesis. Mu1 is greater than mu2. And right away, we can go ahead and state that this is going to be a right-tailed test because it says greater than. And by the way, when you're making your hypotheses, you always want to start with the first population compared to the second, because if you started with the second compared to the first, it would reverse the order of everything. And you may get the same results if you're careful. You would just have to switch this also. So always try to do first, second, or more importantly, be consistent with the ordering of your subscripts in case they're not numbers. So what's the null? Well, we're not given one. And what do we do when we're not given an explicitly stated null hypothesis? We assume it says equals. It would actually be technically correct to say less than or equal to, because these two hypotheses couldn't be true simultaneously. But I don't think somebody's going to assume that unpolluted land yields less potatoes than polluted land. What they might say is it doesn't matter, and if it doesn't matter, then they would be equal. The status quo, if you will. But in the absence of a clearly stated null hypothesis, we assume it says equals. All right, so there's our first step. Our second step is to sketch our regions. Being a right tail test, we're going to cut off the right tail. The non-rejection region always includes the middle, and the rejection region is whatever tail or tails we shaded in. And we need to find the t-score that separates the rejection from the non-rejection. We need to find our critical value. But we're missing one key piece of information. In order to find the t-score, we need to know both the degrees of freedom, which we'll calculate in a moment, and the area of that tail. But the area comes from the significance level, and nowhere in this problem was the significance level stated. There was not an alpha given. Do you remember what we do in the absence of an explicitly stated significance level? In the absence of an explicitly stated significance level, you assume that it's 5%. In fact, there are some books that don't even bother giving a significance level ever. They just lock it in at 5%. It doesn't have to be, but we will do that. In the absence of an explicitly given significance level, you assume it's 5%, which means the area of this tail as a decimal is 0.05. Now we use the degrees of freedom, but the degrees of freedom is the smaller of each sample size minus 1. So to get the degrees of freedom, we just have to go to the smaller sample size. 12 minus 1 is 11. Our degrees of freedom will be 11. And so we go to our chart, which I have here next to the camera. And we go to the 11th row, and we look in the 5% column, which is the second column. In the 11th row, second column, the t-score is 1.7959. 1.7959. And step 2 is done. Step 3 is the calculations. To calculate our test statistic, first we need to calculate the standard error, which will be the square root of the sum of the ratios of the squares of the standard deviations to their sample sizes. I know that was a long prepositional phrase. This formula. The square root of the sum of the ratios, so fractions, of the squares of the standard deviations. The first one was 0.35, so that will get squared. And the second one was 0.24, that will get squared. The square root of the sum of the ratios of the squares of the standard deviations to the sample sizes. The sample sizes were 30 and 12 respectively. Calculator comes out and we round that to 4 decimals. I invite you to pause the video and try to calculate that yourself just to make sure your calculator skills aren't letting you down. And I will calculate it twice just to make sure I didn't make a mistake. I am human. To 4 decimal places, I got 0.0943. But let me do it again, and this time I'll call out my moves. 0.35 squared divided by 30 plus 0.24 squared divided by 12 equals, and square root that, and I got the exact same thing. It was actually 0.0942, but the next digit was 5, so it rounded up. So we use that for our standard error. Let's put a box around it so it doesn't get lost. And for our test statistic, it will be the difference in our sample means, but it has to be in the same order as here. That's important. The difference in the sample means has to be the same as the order we compare the means here. So x bar 1, 10.2, minus x bar 2, 8.1, divided by our standard error, 0.0943. Let me make this 8 a little bit better. And we'll round that to 4 decimal places. 10.2 minus 8.1 equals, and divide that by 0.0943. And as simple as it may seem, wow. As simple as it may seem to put this in your calculator, you'd be surprised how many people do it incorrectly. I got 22.2694. It was actually 93, but the 3 rounded up. I strongly recommend pausing the video right now and putting this in your calculator to make sure you get that value, because some people won't. Some people will put it into their calculator incorrectly, and they'll get negative 75.6961. I don't know if it's focused or not. But if you got negative 75.6961, then what you did is type 10.2 minus 8.1 divided by this decimal. And when you do it like that, you're only dividing the 8.1 because your calculator knows the order of operations. In other words, we have to complete the subtraction before we do the division. There's 2 ways to do it. Number 1 is to put parentheses around the subtraction problem. Number 2, do the subtraction problem and press equal to get its answer, and then divide by this. But I'll do it one more time just to make sure I didn't make a mistake. 10.2 minus 8.1 equals divided by 0.0943. Yeah, I got the same thing. That's what I said, wow, because that's a pretty large test statistic. And remember what we do with this guy. The next thing we do is we compare our test statistic to our critical value to see which region it lands in. Well, our critical value that separated our regions was a paltry 1.7959. The test statistic is so far to the right, we can't even see it. But it doesn't really matter how far to the right it is. It's just the fact that it's to the right puts it in the rejection region. And so our conclusion is we reject the null hypothesis. And to answer our question, can you conclude unpolluted land yields more potatoes? Can we conclude mu1 is greater than mu2? Well, we rejected the null hypothesis, which means we accept the alternative in its place, and that's what we're being asked if we can conclude. So to wrap this problem up, yes, we can conclude unpolluted land yields more potatoes. Unpolluted land yields more potatoes. Which I can never remember if it's spelled with an O-E-S or an O-S, so I wrote it both ways just in case. Having flashbacks of Dan Quayle. Most of you probably don't get that. YouTube, Dan Quayle potatoes, and you'll see what I mean.